Welcome, ladies and gentlemen, to our continuing study of DC circuits. Today we are going to look at what is called a parallel circuit. Unlike a series circuit in which there is only one path for current to flow, in a parallel circuit there are multiple paths. And the paths are more or less independent of each other. Okay? What that means is they each enjoy their own connection to the battery. Okay? I can make a full loop here. Okay, let me draw that. I can go from the positive end of the battery all the way around to the negative end with R1, with resistor 1. Okay, resistor 1 is completely independent of resistor 2 and resistor 3. Okay, and each of those resistors, right, they have their own separate loop to the battery. Okay, each of those enjoys their own separate loop to the battery. And as you're going to see in a little bit, what that means is they get to each enjoy the full voltage of the battery. Okay, so in a parallel circuit we have multiple paths for current. All right, and you're going to see that current and voltage behave differently than they did in a series circuit. Okay, in a series circuit there was only one current, so all the resistors had to have the same current. But in this case you can see there's an I1, an I2, and an I3, and each of those currents is different depending on the resistance in that branch. Again, the less resistance, the more current there is, right? Ohm's law. So the way we can represent the behavior of current in a parallel circuit, okay, is like this. We can say that the total current, which again is the current coming out of the battery and back into the battery, we call that I, or you could call it I total, okay, is going to be the sum of each of the individual currents, okay, the sum of each of the individual currents. All right, voltage. Again, the total voltage, okay, can be related to the voltage across each of the resistors in the following way. They're all equal to each other, okay, because each resistor is separately connected to the battery. So each resistor gets to enjoy the full 20 volts, okay, unlike a series circuit where the resistors have to share the total voltage, okay. If you'll notice, these two expressions are exactly opposite what they are for a series circuit. Okay, finally we want to talk about resistance. Okay, and when we talk about the overall resistance of a circuit, you could call it the total resistance, or another term you'll see is the equivalent resistance. Okay, hopefully you discovered the behavior of resistance in the lab already. Okay, but you may have been surprised by the behavior. Okay, unlike with series circuits, when you add resistors in parallel, the overall resistance actually gets less and less, okay? And that has to do with the fact that you're adding more paths, right? More paths means more opportunity to flow. More opportunity to flow means less resistance, okay? So what we need a math relationship where when we add more R's, the overall number actually gets less, okay? And what that looks like is this, and this is a new relationship, okay? 1 over, we'll call R total here. We're just going to add the reciprocals. Okay, we're going to add the reciprocals like that. And this equation works for however many resistors you have. Okay, that's called the equivalent resistance of a parallel circuit. Let me illustrate the behavior of current here with some arrows so you can get an idea of what happens. Okay, coming out of the battery, we have this full current I, right, which is the total. Okay, now when it gets to this point here, right, or this point here, these are called junctions or branches, right? You're going to see current split off, right? In terms of coal cars, some are going to go along this branch, but others are going to continue down, right? And then when we get to the second junction, some are going to go off and some are going to continue down, okay? And then the same thing is going to happen on the other side, except the currents are going to add back together, right? You're going to have a certain amount of coal cars here, and it's going to be joined by those. And then you have a bigger total here, and it's going to be joined by those. And then the total number of coal cars going back into the battery will be the same as going out of the battery. All right, what we're going to do now is actually treat this circuit as a problem to solve. Okay, and again, as with the series circuit, we want to be able to solve for voltage, current, and resistance in any and all parts of the circuit. So let's see what that looks like on the next page. All right, so I have the same circuit again, and I'm going to take the same approach. I'm going to Ohm's law this circuit to death. Okay, I'm going to start with the totals again. In other words, I'm going to find the overall voltage, the overall current, the overall resistance, and then go and find the voltage, current, and resistance in each part of the circuit. There's actually two ways to do this problem. There's an easier way. I'd rather show you the harder way, okay? And then maybe we can talk about the easier way on your own, which you probably could figure out anyway. All right, so the overall voltage of this particular circuit is 20, right? Now, in this case, we have two unknowns. We don't know the overall current, and we don't know the overall resistance. So what we're going to do, actually, is we're going to come over here, and we're going to use this brand new overall resistance formula, okay? And it's just 1 over each of the resistors, right? So the first one is 4 plus 1 over 2 plus 1 over 6, okay? Now, some of you are a little rusty on fractions, okay? Good news for you. There's a real simple way to do this in a calculator, okay? And that is, all you do is you use the x to the -1 button, right? So you'll type 4x -1 plus 2x -1 plus 6x -1, just like that. And then you'll get a decimal answer, okay? And you can go from there. I'm going to go ahead and do it the fraction way, right? So you can dust off your fraction skills. We need a common denominator here, okay? It's going to be 12, and we can add all these together here like so, and we will get 11/12, okay, as an answer, right? I need to pause here. This is where all your mistakes will happen with parallel circuits. You will add the fractions and think you are done. But notice that it does not say R total equals. It says 1 over R total equals, okay? That means that we need to flip both sides. We need to reciprocate them. And what we get then is a total of 12 11ths, right? 12 11ths in the symbol, the unit is still ohms, okay? This comes out to about 1.1 ohms, all right? Now we can bring that over here back to Ohm's law, right? And we can put that total resistance right here, okay? And we can solve for the total current coming out of the battery. Now, before I proceed, I want to point out something to you. Notice that the total resistance of the circuit is less than the smallest resistor in parallel, right? 1.1 is less than the smallest one, which is R2, 2 ohms, okay? Remember, as you add resistors in parallel, you get less overall resistance. All right, when you solve this mathematically, you get 18.3, and again, the unit is amps, okay? And that's this number right here, right? 18.3, and also here, okay? Now, that total is going to split as it reaches each of the junctions, okay? Now what we can do is apply Ohm's law to each branch, right? R1, R2, R3. We'll do that right now, V1. Okay, I'm just going to pause and write them all out. Okay, we are going to apply Ohm's law to each branch. Now remember what I said earlier, each branch enjoys its own connection to the battery, so each resistor gets to enjoy the full 20 volts, okay? And then we just have 3 simple math equations to solve. 4 ohms for resistor 1, 2 ohms for resistor 2, and 6 ohms for resistor 3. Like that. And when we solve this, okay, we're going to get 5 amps, 10 amps, and 3.3 amps. Like so. Okay? So I'll just write the numbers here. 5 amps, 10 amps, 3.3 amps. What do you think all these numbers add up to? That's exactly right, the total current. Okay? Notice also that in the second branch, right, there's twice as much current as in the first branch, right? 10 amps versus 5 amps, and that's because the resistance is half. Remember that Ohm's law is a proportional law, right? When you double one, you double the other, or in the case of current and resistance, they're inversely proportional, right? So when you double one, you half the other. All right, the last thing to do is to coal mine analogy this circuit. All right, so I'm going to pause again, go to the next page, and set up the coal mines, and we'll talk through their values together. You're going to see more coal cars than in a series circuit. We got more branches, right? So what we're going to do is we're going to put the multipliers for the current onto each of these cards, right? We had coming out of the battery, right? We had 18.3. And then coming into the battery, same thing, 18.3. Okay. In the first branch, we had 5. Second branch, we had 10. Third branch, 3.3. And we could add those to each branch, like so. So there's that. That's the current, right? Now, the part that's new here, okay, is what's left over after one of the branches takes some away. Let's go back to the top here, 18.3. Right? When 5 carts every second go into this first branch, what's left? That's right, 13.3. Okay? So these here need to have the 13.3 multiplier, right? That's how much running, that's how much this current is going in that part of the circuit right there. And I'll erase this, but that part of the circuit right there, okay, is 13.3. All right, and then finally we need to put the coal in, okay? 20 joules, right, it's the 20 volt battery. Okay, let me have 20 volts here again. So 20 joules, 20 joules. All these on the left side are full, right? They haven't hit any power plants yet, like so. Okay, and then on the other side, I'm just going to leave them empty, right? They all go through their power plants, light bulbs, and I noticed, by the way, that I changed to light bulbs from resistors. We'll talk about that in a minute. You may have noticed that I changed from resistors to light bulbs, okay? And now I want to wrap up this lesson with a brief discussion of which light bulb you think is the brightest. It is indeed the middle one, the one with the most current, okay? The one with the most current will also be the one with the most power. So if you do a power calculation by branch, right, P equals IV, okay, remember each of these branches has 20 volts, right? So the one with the most current is going to have the one with the most power.